So today we're going to start a new topic with power functions. And our basic idea with power functions, as we can see here, it's going to be any function in the form of a times x raised to the b. So that's our basic idea of a power function. A and b are going to be real numbers, and they're not going to be equal to 0. Okay. So for each of these below, we're going to state the value of a and b by writing the equation in the form a times x to the b. So we want to get this out of the fraction first. So now we got to go back and we have to think when we're going to take this out of the fraction, our exponent will become negative. So now I have it in that form of a times x to the b. And so I can see here my a value is now 3, and my b value is now going to be negative 2. Okay. Try it again with letter B. Now again, it needs to be out of that root, so I have to go back to my root concept, and I could rewrite this as x to the 1/2. Keep in mind, since it's a square root, that root value goes on the bottom, the exponent with the variable goes on the top of that fraction. Okay, so again, if I'm thinking I want to put this into a times x raised to the b, and I'm looking for the a value is 8, and our b value is 1/2. Here we got one more, kind of a combination of both. We have to take it out of the fraction, out of the radical. I'll go 2 steps here. So if I'm looking at this fraction and I want to take it out of the radical first, I'm going to have x to the 1/3. Now taking that out of the fraction, I have 6 times x to the negative 1/3. Okay, so again, if we're looking at this concept of a times x to the b, we can now see our a value is 6, and our b value is going to be negative 1/3. So that's the idea behind our power functions, what a power function looks like, how we can transform them. Okay, and depending on the value of a and b is going to depend on what our power function is doing and what it's going to look like. So considering this general power function, okay, we want to figure out what can be said about the y-intercept of any power function so long as b is greater than 0. Okay, well, we've answered this y-intercept question a bunch this year, and to find a y-intercept, you're going to make x 0. So by making x 0, now I have 0 raised to the power of b, and when I simplify this down, I can tell you that the y-intercept has to be located at 0, 0. Okay. And if I'm looking at letter B, then it says, what can be said about the y-intercept of a power function this time if b is less than 0? Okay, well, for instance, if b is less than 0, let's think about maybe this kind of a concept, x to the negative 1. So if that's the case, if we were to turn this back into a function without a negative exponent, that would get us something that looks like this. So now if I said, let's find where the y-intercept is and make x 0, now our function, I have a 0 in the denominator. And we can't have this happen here. Okay, this would give us an undefined. So we can't make x equal to 0. All right, so what would we say here? We would say the y-intercept does not exist. So when we see DNE, that stands for does not exist. Okay, so y-intercepts, we know are going to be at 0 for our power functions unless we have a negative b value. So with that idea, we're looking at this whole thing. Rather than having you fill this out, I filled this out for you. So it says we're just going to concentrate on power functions where the exponent right now is a positive whole number. And I want you to look at this chart, and I want you to try and see maybe some patterns that we're seeing here. And notice the big difference between your even exponents, okay, versus when we're taking a look at your odd exponents. So that's really what I want you to focus in on. Okay, so your even exponents, if you're noticing, when x is both a negative and a positive, I can see here, so x being negative 1, I get 1, x being positive 1, I get 1. Okay, x being -2, I get a +4. X being +2, I get a +4. So check that out for x to the 4th. Okay, notice what happens. If we have our inputs are opposite numbers, negatives, positives, I still get the same output back. This should be kind of sounding like an even function. Okay, so if we think about our even function, not only are our exponents even, but the function itself is even. Okay, that even concept that we had was that idea that if I had an x value, I would get out the same thing as if I plugged in a negative x value. Okay, different now when I'm looking at these odd exponents. So it's 3 and the 5. So again, let's just even check out the 1s, right? So if I'm looking at the 1 and the -1, notice what happens here. I input a negative, I output a negative. I input a -2, I output a -2. But if I input a +1, I output a +1. And if I input a +2, I output a +2. Okay, and same thing with the 5. So again, that's kind of sounding to me like if I input a negative, I output a negative. If I input a positive, output a positive. Those are sounding like your odd functions. So again, not only is your exponent odd, but now it's going to start to behave like an odd function. Remember that idea with odd function. Our negative input, or if I negate an entire function, will have the same output. Okay, so again, another thing to take note of that we didn't see on this table or we didn't mention yet is your y-intercept. Like we had mentioned before up above, it's all going to be 0. Okay, so let's try and take this idea of our odd and even functions. And we're going to take a look. It says from the previous exercise, what we just looked at, we should note that when the power function has an even exponent, then the positive and negative inputs have the same value. So when the power function has an odd exponent, the positive and negative inputs have opposite outputs. And that's what we said, it's the definition of our even and odd functions. So we could use our calculators to sketch the power functions below, and we could check out what we're going to get. I'm hoping we don't need our calculator to graph just a plain old x squared. So plain old x squared, we would have something that would look like this. If we look at our calculator for our x cubed, okay, notice the end behavior on this graph. So your x cubed graph is looking something like this. Okay, so they're pointing in opposite directions. Now here we're back to x to the 4th. Notice it looks very much like a parabola, but it's flattened out in the center. Okay, so your x to the 4th graph is going to be a little bit flatter and then come out. And again, same thing here, a little bit flatter and then come out. And then guess what's going to happen with your x to the 5th graph? Looks like x cubed, but again, notice that middle section looks a little bit flatter. So again, if we were to graph this out, we'd have kind of a flatter section, and then it would come back up. Okay. I guess notice your end behaviors on these. Notice your even functions are both pointing in the same direction. So if I have an even exponent, they're both going to be pointing in the same direction. Where if we have an odd exponent, okay, or an odd degree, then I know they're going to be in opposite directions as far as their end behavior goes. So I know right now an x to the 6th graph should look just like an x squared or an x to the 4th, both pointing in the same direction. Now the other thing you want to keep in mind is we've always talked about that a term, the number in front of our first term. If that's negative now, I would get a different graph, and that graph would now be pointing down rather than pointing up. Same thing with a cubic graph. Okay, so let's just give you a different example here. If I had if I had a negative x squared, well now I know my negative x squared looks just like what it would be, except for flipped. Okay, same thing if I had a negative x cubed, well it's going to be flipped. Okay, so those negatives, all it would do is just change the direction of your graph. So with that in mind, and taking a look at number 5, it says, which of the following power functions is shown in the graph below? Okay, so I know it's pointing in the same direction, which means I could eliminate choice number 1 and choice number 4 because they both have odd exponents. Okay, so I'm looking at choice 2 and looking at choice 3, and I see they both have even exponents. So now the next thing you want to do is you want to check out that A term. And because it's pointing down, I know it has to have a negative coefficient. So choice 3 would be our answer here. Okay, moving on to the end behavior. So taking a look at, I've mentioned this end behavior, what's going on at the ends of the graph. And so we're going to take a look at 2 functions that I have graphed for you. So we're going to take a look at this function and then our basic x cubed function. And the idea here is I'm going to show you 4 different graphs. And notice what happens with our windows. The windows are going to get bigger and bigger and bigger. Okay, so we're going to start off with a basic graph. And here's our basic graph. I got x cubed is red and the x cubed negative 2x squared minus 29x plus 30. That's in blue. So that's our original window. Now making my window bigger, in other words, zooming out, notice what happens. They're both cubic graphs. It's just that first one had a whole bunch of extra stuff going on. But once I make my window bigger, they start to look alike. And if I extend it out more, the larger my window, the more similar they get. And even more, same deal. The larger the window, the more similar they get. So if I'm thinking about this, it's asking us, what do we observe about the nature of the 2 graphs as the viewing window gets larger? Okay, so as it got larger, we could say the more complicated or complex, okay, so that one that had all the extra stuff besides the x cubed, it started to look like that x cubed graph. Okay, so the more you zoomed out, the larger that window got. Our more complex graph, which I believe was our first one, that was our y1 graph, started to look more like our x cubed graph. Okay, when I looked at their final window where it was super big, they looked pretty much to be the same. Okay, and so why is this happening? Well, as our x value gets larger, x cubed is going to dominate. So as x gets larger, x cubed will dominate. Meaning it's going to kind of take over. It doesn't really matter what's going on with the rest of the graph. That x cubed is going to grow so fast that the rest of the graph is just going to kind of peter out. It's not going to matter. It's going to dominate, we can say, like all the other terms. Maybe we'll clarify. It's going to dominate all the other terms. Meaning when I have an x cubed graph, no matter if it's just plain old x cubed or x cubed with a bunch of other things happening, in the end, it's all going to have that same looking graph. Okay. The end behavior, also known as long run of any polynomial, is dictated by the highest powered term, or what we call the degree of the polynomial. So I can say that this is a degree 3 polynomial. Okay. I hope that gives you a basic idea of some power functions. Bring your questions to class and we will go over it tomorrow. Hope you guys have a great day.